Listo. Ok, voy a cambiar inglés porque es más fácil así.
Claro, adelante, Mauricio. Thank you very much.
Okay. Gracias a ti. All right. Hello, everyone again. Thank you for being back for part 2. So this is where I'm going to talk about, first, yesterday I talked about what the basics were about high energy cosmic neutrinos and what we have learned about them, mainly from IceCube. Today, what I'll do is tell you about what we have inferred from what we have measured on two fronts. The first one is astrophysics and the second one is particle physics. And then I'm going to say a few things about what we expect to be there in the next couple of decades. So just to recap, neutrinos are exciting, high energy neutrinos are exciting because, as I said, they have the highest energies we've seen so far. So up to PeV so far. Maybe we'll be able to see in the next decade 1,000 times higher energies, EeV. And they come from very far away. In fact, they come from the observable edge of the universe, so a few gigaparsecs away from us. And that allows us to do particle physics and astrophysics in energy scales that would otherwise be unreachable, and looking at sources that are essentially the farthest away that they can be. Okay, so there are two aspects to astroparticle physics. There are two sides of the coin. On the one side of the coin, we have astrophysics, and we take the observations that we have with high energy neutrinos. We try to infer things about the most energetic non-thermal sources of the universe. So things about supernova remnants, blazars, gamma ray bursts, and all kinds of violent phenomena in the deep universe. And on the other side of the coin, there's particle physics. And then we take the same observations and we try to infer things about now fundamental physics. So new neutrino interactions and the properties of neutrinos at high energies. And of course, these are linked by this high energy astrophysical neutrinos that we have been talking about. And with that in mind, let's dive in and see what we have learned about astrophysics so far. So again, this is the first side of the coin, the astrophysics. So as we said yesterday, we don't know where the high energy neutrinos that IceCube has seen are coming from, but we have good guesses. And we believe that the sources look something like this: a compact object with an energetic jet of matter spewed out by angular momentum conservation and by charge conservation. And sorry, I should say by acceleration, by Fermi acceleration mechanisms. That's what I wanted to say. Along the jet, there's matter moving at Lorentz boosts of up to 100, maybe more. So this is very highly accelerated matter, especially if there's protons that are trapped by high magnetic fields. Those protons are slowly building up their energies to reach energies of 10 to the 21 or so along the jets. If the jet is pointed at us, then the secondary products of the protons interacting with the matter around the jet could reach us. And we're lucky we have the detectors to see them. That includes the gamma rays that are created along the way and the neutrinos that are created along the way from the proton interactions. Now, as I said, we don't know what the sources are of high energy astrophysical neutrinos, but we do know that whatever they are, they're most likely also the sources of ultra high energy cosmic rays. So we've been talking about, if you remember yesterday's lecture, accelerating cosmic rays or protons, I should say, up to very high energies and allowing them to interact with photons or with surrounding matter to create neutrinos. And that harkens back to the fact that ultra high energy cosmic ray sources should be wasteful. So if we compare our own man-made accelerators versus the accelerators made by nature, there are notable differences. So the man-made accelerators are very clean in the sense that the acceleration happens in vacuum, whereas in astrophysical accelerators, it happens in a medium. So the particles that are being accelerated are interacting all the time. The electromagnetic fields in man-made accelerators are ordered. We need to build the magnetic fields just the way we need to in order to keep things trapped. Whereas in astrophysical accelerators, they are messy. And the beam dumps, so where the accelerator particles interact, in our accelerators, they're precisely regulated, and we allow beams to interact only in certain spots in an accelerator, and we build detectors around those spots. Whereas in astrophysical accelerators, these beam dumps are fully unregulated and happen everywhere and all the time. So that means that astrophysical accelerators, like the one I just showed before, they inevitably make high energy secondaries, and those secondaries include neutrinos. So by studying the secondaries, we're learning things about the acceleration mechanism, the production of cosmic rays, the acceleration of particles up to the highest energies. And though we don't know what the sources are, we do know what the sources need to satisfy in order to be sources of cosmic rays. And that is called the Helix Criterion. And it was first introduced in the early 80s by Helix. This is a necessary but not a sufficient condition for a source to accelerate cosmic rays up to the highest energies. And the main idea is that the particles, the cosmic rays, must stay confined while they're getting accelerated. So the size, their gyro radius or their Larmor radius moving inside a magnetic field has to be smaller than the size of the region in which they are being accelerated. Otherwise, they would have left the region and they wouldn't be accelerated anymore. And when you do the math, this translates to size of the region. Sorry, the Larmor radius has to be smaller than the size of the acceleration region times some Lorentz boost, because we're transforming reference frames. So this number can be anywhere between a few and 100. And in turn, you can then find an expression for what the maximum energy is for a source that is accelerating cosmic rays, that has a certain magnetic field, and where the medium in which the protons are being accelerated is moving at a certain speed given by the Lorentz boost. Turns out that this energy is roughly 3 × 10⁻20 electron volts, and it has a dependence that is proportional to the size of the accelerated region and to the magnetic field in that region. So this is just a necessary condition for us to reach a certain energy. So if you want to reach, say, if you're talking about protons, because here the charge matters, right? Protons has a Z of 1. And you want to accelerate the protons inside a source to energies above 10⁻20 electron volts, then you need to satisfy a combination of magnetic field strength and size of the accelerating region that is above the solid red line. That's where the Helix criterion is satisfied for a particular speed of the outflow where the interactions are happening, where the acceleration is happening, sorry. And that means that we have a few candidates that actually satisfy this condition on the magnetic field and the radius or the size. And that includes neutron stars, high luminosity GRBs, low luminosity GRBs, tidal disruption events, and a few others like active galactic nuclei. And some of them actually do not satisfy the condition, like supernovae, some normal galaxies, maybe not. Galaxy clusters are, depending on their properties, might or might not. So this is just a handle that we have to start building a few candidates of which could be the sources of ultra-high energy cosmic rays. But there are things that are not accounted for here, like protons can also lose energy while they're being accelerated by interacting with the medium, by synchrotron radiation. So the Helix criterion is necessary, though not sufficient. All right, so going beyond that, like a very general criterion, I like to think about the strategies to find neutrino sources along 3 lines. So the first one is, remember, neutrinos are produced together with gamma rays by the proton-photon interactions. And then it makes sense to look in the sky for the brightest gamma ray emitters. So we can look at the brightest thing in the sky and look at our neutrino data and see whether there's correlated to that gamma ray emission some neutrino observations in that same direction for that source. Or we can take a few possible candidates that individually would not be detected in neutrinos, but maybe if you put them all together, you might see a fluctuation over the combined background of atmospheric neutrinos that all of these would have. And in both cases, we have not seen a prominent steady state emitter. That means emitter of neutrinos that is making neutrinos constantly, but we have 2 likely transient emitters, and I'll talk about that in a second. And they are also bright in electromagnetic emission, which is what we wanted to do in this criterion. The second way to find sources is for looking for neutrino multiplets. So if you look at the sky and you see a region in the sky where you're getting pairs, triplets of 4 plets, multiplets of neutrinos along the same direction, then that might be telling you something about whether there's a source or a group of sources in that direction. So we can look for clustering of neutrinos in a certain direction, or we can look for clustering of neutrinos in a certain direction in a small period of time. And in both cases, we haven't seen any clustering, both in direction and in time. And this will come in handy when we talk about short-lived gamma ray transients. I'll say more about this in a bit. And finally, we can stop looking at individual sources or looking for multiplets and look at the diffuse neutrino flux, which is the one thing we have clearly seen. Remember, we have seen this at more than 7 sigma significance over the background of atmospheric neutrinos. So whatever the candidate, whatever the population of sources or populations, in plural, of sources of the neutrinos they must produce neutrinos in such a way that they can account for the diffuse neutrino flux that IceCube has measured with the same shapes and the same properties. So that puts an indirect constraint of what the sources of the neutrinos could be. And that it's a combination of all these 3 strategies that is trying to find the sources of neutrinos. Okay, so let's talk briefly about looking for neutrinos coming from electromagnetically bright point sources. And that is a well-practiced endeavor. IceCube does it in the South Pole, and Antares does it in the Mediterranean Sea. Remember, IceCube is bigger, so the IceCube is the only one that actually has seen a signal from astrophysical neutrinos. Antares hasn't yet. And what you see here is the sensitivity or upper limits in some cases, depending on what you see here in the legend, to a flux of neutrinos as a function of the sign of delta here. And this is the declination. So all of these sources have negative declination. That means there are sources located in the southern sky. So they are over here. And I want you to remember from yesterday that if your detector is in the South Pole, like IceCube, you're very sensitive to sources that are in the northern sky, because those neutrinos from the sources would arrive to IceCube, whereas the atmospheric muon background created in the opposite side of the Earth would be filtered by the Earth. Whereas Antares, which is in the northern hemisphere, is sensitive to sources in the southern sky for the same reason. So for sources that are very much in the southern sky, so over here, then Antares dominates in sensitivity. You see here that the best sensitivity is coming from the dashed red line from Antares. And for sources that are a bit away from the southernmost direction, then IceCube starts dominating just because it's bigger. So it's when you look at sources that are over here, for instance, then IceCube does better than Antares. But anyway, so we expect this to improve in the future by about 1 order of magnitude to go down over here or so. And that would actually start revealing any sources that could be maybe in the Milky Way, for instance, because we expect sources to be at that level if they exist within our own galaxy. But so far, nothing is popping up. Okay. However, you can use that information, the upper limit on the neutrino point source emission, to say something about the population of sources as a whole. So let's assume that the closest source to us is emitting neutrinos with a certain fluence, this fluence over here. And this is, like I said, a benchmark number that we expect to reach quite soon. What does that mean? It means that we have 2 things to try to explain. The first one is you need to explain the diffuse flux that IceCube is seeing. And in order to do that, the neutrino luminosity of a single source has to, and the number density of the population of sources, each one emitting with this neutrino luminosity, has to be able to explain the diffuse flux. So the sources, whatever they are, they need to lie within this purple band, because that satisfies the observation of the diffuse flux that IceCube has made so far. So you have here low luminosity active galactic nuclei, starburst galaxies, radio quiet active galactic nuclei, radio loud AGN, BL lag galaxies, flat spectrum radio quasars over here. That's one thing. But then whatever the sources are, they need to be on this purple band. But also there's a sensitivity that we've been talking about, this 10 to the 9. And if IceCube doesn't see anything, hasn't seen any point source popping up in the sky, it means that we can kill this part of parameter space, the one that is in the darkest blue. All the things to the right would can be now excluded as the actual sources of neutrinos, because then we would have actually seen a flux coming from one of them. And in the future, with a bigger IceCube or IceCube Gen 2, we can start killing more potential source candidates. We're moving this constraint line to the left and killing more and more candidates. So this is a game we can play by not observing neutrinos from point sources. We put limits on the effective neutrino luminosity of each source and on the local density, number density of each source. Yesterday, we talked briefly about PeV neutrino sources in the Milky Way. So what is the contribution of sources within our own galaxy to the diffuse flux that we've seen? We talked about how this is done. We have several possible sources within the Milky Way that could be making neutrinos, like pulsars or the black hole in the center of our galaxy. And we look for neutrinos in those directions in IceCube data. And in fact, there's no correlation so far. So if there is any contribution coming from galactic sources to the diffuse neutrino flux, it is lower than about 14%. I think now it's even smaller than that. But it doesn't mean it's not there. It could be there. In fact, you might have heard about the recent announcement by the Tibet AS Gamma collaboration of the first detection of PeV galactic gamma rays. And you would expect maybe those same sources that are making the PeV gamma rays in the Milky Way are also making neutrinos. And some people, of course, thought about that. Turns out that, again, whatever the contribution is of those sources is not more than 10%. So it's going to be a bit hard to find them, but not impossible in the next generation of detectors. Okay, so we've been talking about the fact that if you see a neutrino, a source that is bright in gamma rays, then it's likely to be bright in high energy neutrinos as well. Because if you remember, the photohydronic interactions that give rise to high energy neutrinos also give rise to high energy gamma rays. That is true, but the situation in reality is a bit more nuanced than that. So there are some fudge factors here in the proportionality between the energy neutrinos and the energy in gamma rays. It includes the source properties, like how much energy is given to the protons that are being accelerated, what is the density of the sources, is it evolving in time, et cetera, and the particle effect. So we don't know the neutrino producing channels or interaction channels change with energy, for instance, and sometimes some of the, as we'll see in a moment, some of the cross sections that are involved in the particle in the neutrino producing chain are not known very well, so we have to make guesses. So the correlation is a bit more nuanced between the energies of the three messengers, neutrinos, gamma rays, and cosmic rays, but it is there. For instance, the sources that make neutrinos via proton-photon interactions may be also opaque to gamma rays, because if you want to make many neutrinos via these interactions, it means that the densities are very high. That means that if you make gamma rays, they will quickly interact inside the source and won't be able to reach the source, to leave the source. And on the other hand, this is what I was referring to a few seconds ago. We don't know exactly the cross sections for all the processes involved in proton-photon interactions and the nuclear cascading. So if you have not a proton but a heavier nuclei interacting with the surrounding matter or surrounding photons, then they will create lighter nuclei by breaking this nucleus, and then there's a nuclear cascade of lighter isotopes being created, and there are some cross sections that are not known very well, and that affects the neutrino emission. So there are some important nuances here that need to be taken into account. But in general, just to illustrate this, again, we expect the energy in neutrinos coming from a source should be proportional to the energy in gamma rays coming from that source. So energy in neutrinos on the left, energy in gamma rays on the right, and in between there's all the mess, all the physics. And this number over here is the fraction of the total proton energy that is of the protons that are interacting, that is given to the pions that then decay and make the neutrinos. So there's one key number here that's that in one single proton photon interaction, how much energy does the pion receives from the proton? It's about 20%. So the remaining energy in the, say, the proton lot in the source is 1 minus that, and that the protons may on average interact more than once. And this is a bit of a delicate argument, but this number then it can be further decreased by multiple interactions. That's why you are elevating it to some number of interactions the protons undergo inside the source. And then you want to know how much remaining energy is after all of these interactions, and that's what the neutrinos receive. And there's one further handle here. It's called the baryonic loading. It's very uncertain. It's the fraction of the total energy available in the source given to the protons that are making the neutrinos compared to the fraction of energy that is given to the photons or the electrons inside the source. And this number, this ratio is very poorly constrained. So, and you see that it's controlling proportionally the energy neutrinos and the energy in gamma rays. So the number of times a proton interacts inside the source, which is directly proportional to the number of neutrinos that one proton on average produces, is going to depend on the properties of the source, the luminosity of the source, the time scale within which the things are moving inside the region of neutrino production, the Lorentz boost of the source, and if there's any break in the photon spectrum with which the protons are interacting, that also comes into here. So this is just to illustrate that the situation is a bit more complicated than just equating energy neutrinos and energy in gamma rays. So there's some nuance here. But anyway, so this is what we expect these sources to look like. If you want to delve a bit more into how the dynamics of these sources are, a good starting point is the GRB fireball model. GRB means gamma ray burst. And this is like a toy model for any source that is jetted, that has a relativistic jet coming out of it. So we have a compact source like a black hole. And then there's an emission of relativistic matter along a jet. And you see that there are some regions inside the jet that are more dense than others. So these shells of dense matter are traveling down the jet at different speeds. Eventually, two of them can catch up to each other, collide. Part of their kinetic energy gets converted into particles, including gamma rays and neutrinos. And those, if the jet is directed towards the Earth, those are particles that we could, in principle, detect. All right. So we can produce neutrinos, gamma rays, and photons also because the protons are being accelerated along the jet. Of course, that explains how we believe how gamma rays work. These are very short flashes of gamma ray explosions when a supernova that is particularly energetic occurs. But it also explains the dynamics of bigger objects like blazars, which are bigger supermassive black holes that are active and are also spewing out matter in jets. So what IceCube did was, of course, we have a very long catalog, a very big catalog of these two types of sources, gamma ray bursts and blazars, with the positions in the sky. Gamma ray bursts occur at over a few seconds. Blazars have a much longer duration, and they are active in a steady state for any human time. They're active for a very long time, so we can count them as being steady state. So IceCube looked in the direction of gamma ray bursts, it looked in the direction of blazars and tried to find correlations between the positions of these objects and the incoming direction of neutrinos, and they found none. So what you see here, I'm not gonna go into detail much, but let's just focus on this one. This is the flux that IceCube sees in blue, in dark blue. This is neutrino energy in the x-axis, flux in the y-axis. And the upper limit on the contribution coming from gamma ray burst, all of the gamma ray burst, is this black line over here. So you see that it is about less than 1% of the total diffuse flux. So if gamma ray bursts are sources of high energy neutrinos, they're very, very weak sources, and a similar argument holds for blazars. That said, we're talking about steady state sources in the case of blazars, but we have seen one blazar flaring, and flaring in electromagnetic emission and in neutrinos. So in 2017, IceCube found one neutrino of about 300 TeV coming from the direction of a flaring blazar. This blazar called TXS 0506 plus 056, the Texas blazar. And that was a claimed coincident detection of gamma rays or X-rays, sorry, and neutrinos. And when that happened, they looked back at their archival data and found that in 2014 and 15, there was a coincident detection of about 13 plus minus 5 neutrinos coming from the same direction. The difference is that back then in 2014 and 15, there was no associated X-ray flare when these neutrinos were detected. So 2017, coincident detection of X-ray flare and 1 neutrino, 2014, 15, neutrinos associated to the blazar, but no X-ray flare. So if this is an actual source of neutrinos, then it is the first claimed detection of a extragalactic point neutrino source. And there's a lot of nuances involved. It's difficult to explain how these same object can behave differently, can make neutrinos at high energies with an X-ray flare and without an X-ray flare in 2 different periods. But it's the first real data point that we have to start thinking seriously about sources. Okay, and the other potential promising source that we've had is a tidal disruption event. A tidal disruption event occurs when a solar mass star approaches a supermassive black hole and gets broken apart, tidally disrupted. At about 50% of the debris is bound around the supermassive black hole, and it can create a flash of X-rays that lasts for a few months, and sometimes it has a jet also. So again, in 2019, there was one such event in April, and it was coincident with 1 neutrino event seen by IceCube with an energy of 200 TeV, which you see over here. Now, in order to explain it, the modeling is a bit more complicated. This is what you see here is a model of the tidal disruption event with multiple regions where particles are accelerated and emitted. But the best explanation is that we have a kind of a funnel that is moving at mildly relativistic speeds, and the jet is moving within that funnel. And when that's going on, photons from the funnel, X-ray photons, are being entrained into the jet. Protons are interacting with those photons and creating neutrinos. That one of those is the one that IceCube saw. But so far, then, those are the 2 best promising candidates. So we've been talking about finding a coincident neutrino electromagnetic emission from single sources. Let's talk about what we can learn from looking at the diffuse neutrino flux. And one thing we tried recently is it goes back to how charged particles behave in a strong magnetic field, like the ones we expect to exist inside the astrophysical neutrino sources. So if a particle is a charged particle exists in a strong magnetic field, they should emit synchrotron radiation, and their energies should be lowered because of that. And in turn, that could imprint itself into the shape and properties in general of the neutrinos that are emitted from a source. So in particular, there's 3 particles with charge that are involved in the production of neutrinos, and that's the protons, the pions, and the muons. Remember, the protons interact with the photons or the matter around them. They create pions. The pions decay, make neutrinos, also muons, and the muons decay further and make more neutrinos. So if you have these 3 particles in a high magnetic field inside the source, in this case, I'm just showing a couple of examples, then at energies where the synchrotron cooling of these particles becomes important, you expect some features to appear on the neutrino flux, on the diffuse neutrino flux. So this is the flux that is coming to Earth from the contribution of the whole population of sources where these neutrinos are being made. Not just one source, but integrated over redshift through the full population of neutrino sources. Each one is behaving in such a way that inside it, we have this proton, pion, and muon cooling. So you see here that you see that we have some kinks that appear in the spectrum of the neutrinos, and some suppression at high energies. Those are coming from the action of the synchrotron cooling of the protons, which exists over here, of the pions, which induces this break over here in the spectrum, and of the muons, which induces changes in the ratio of each neutrino flavor being produced. So we can actually look at the data, at IceCube data, real data, and try to find whether there's evidence of this kind of features, changes in the shape of the spectrum. And we did that using 6 years of data. And as you can expect, because nature is unkind sometimes, we found no evidence. And that means that we can actually put limits on what the magnetic field strength is of the neutrino sources that are making the neutrinos. Whatever these sources are, the magnetic field needs to be smaller than what you see here in this red line. So it has to lie below that red line, and that means that there's a lot of allowed space. You see the different possible source candidates here, but at least some of the tips of some GRB models are being disfavored at the moment by this synchrotron cooling argument. Okay, this is how you can use the diffuse flux and the shape of the diffuse flux, I should say the energy spectrum, to put limits on or to try to find the identity of the neutrino sources. So it's an indirect way. And finally, before jumping into particle physics, let me tell you about what else can you do to try to find the nature of the sources. You can use flavor information. I just mentioned flavor, so let's continue on that. Remember, we had yesterday our picture of sources emitting neutrinos with some combination of some relative number of electroneutrinos, mu neutrinos, and tau neutrinos, which along the way to Earth, they oscillate, and the oscillations are controlled by the mixing parameters that we measure at oscillation experiments. And then we have an expectation for the number of nu e, nu mu, nu tau at the Earth. But we can do the opposite. We can see, we can ask ourselves, what does IceCube, for instance, sees? What does it measure for nu e, nu mu, nu tau? And given that we do know some things about this mixing parameters, we can undo the effects of the oscillations and try to find out what the flavor ratios were when the neutrinos were first emitted at the sources. And that in turn can tell us about the physical conditions that exist inside the sources. So we don't need to know what the sources are. We're inferring the physical conditions that need to be in the sources from the observation of astrophysical of the neutrino flavor ratio. Sorry. So we do that, and there's two ingredients. First is the actual observation of the flavor ratios at the Earth in IceCube, and we can do it with any of. I mean, it's been varied in time, as you see here, and we've tried it with a few of these existing observations, and we've done projections for the next 20 years as well. And of course, in the future, it becomes better and better because the observations get tighter and tighter. And the second ingredient is that we need to know the values of the mixing parameters. So the 3 mixing angles, then 1 delta CP phase. And this is not only are these known to different precisions from global fits to oscillation data, but they are also correlated. And just as an example, I'm showing here the correlation between delta CP, the CP violating phase, and theta to 3, sine of the square of theta to 3 for what we expect Dune to do in the next 10 or so, or 15 or so years. So we've taken that into account. We've seen how these, we did our own simulations about how the sensitivity of these parameters will vary in time as different oscillation experiments turn on. So as you see here, Dune, there's also Juno, there's Hyper-K. We mentioned those very briefly yesterday. And we've also, on the left, we've seen how, well, we've modeled how these sensitivity to flavor measurements will vary with time. And in fact, what you see here is just the 68% containment region, but actually what we have is for every point inside the triangle, we need to assign a likelihood that IceCube would be able to measure that point, and that's what we did. So this is just to show, this shading is just to show that the posterior, or the ability of IceCube or any detector to measure a particular flavor ratio is defined inside the full triangle. And in time, these ellipses become more smaller and smaller as the sensitivity becomes better and better. Okay, so we take the 2 ingredients. Remember, these are our three benchmark scenarios for flavor ratios. The pion decay flavor ratio, we end up close to the center. If muons are losing too much energy before decaying by synchrotron radiation, we only get high energy muons, and we end up somewhere over here at the Earth. And finally, if we make neutrinos, nu-e bars in particular by neutron decay, we end up somewhere here if we know the mixing parameters perfectly. And on the right, what I'm going to show here is I'm going to try to reproduce the value of the fraction of nu-e only, just to make things simple. And I'm going to assume that the real value is, for future measurements, that the real value is the one given by this benchmark scenario, so about 30%. This is my real value. I'm going to try to reproduce that value, given that I see neutrinos, the flavor ratio, sorry, at IceCube with some uncertainty, and that I know the mixing parameters with some uncertainty. So if we use today's measurement of the flavor ratios by IceCube and today's knowledge of the mixing parameters, this is conveyed by this new fit global oscillation fit, then actually the preferred value, this is real data, by the way, the preferred value is not 30%, it's something closer to 0. So that is not so good. And it's a bit weird, but it's fine. It's a very broad distribution. If we use the values that we could, the sensitivity that we could actually have today, if we were to combine all of the available IceCube data, which has not been done yet, it's in the process of being done, then assuming that that flavor ratio measurement will be centered around the center of the triangle, so around our real assumed value, we could reproduce that value poorly. So this is this posterior that you see in a slightly darker blue. So it's not so good. So what this is saying is that roughly today, we can say that there's a slight preference for sources making neutrinos by pion decay, which is what this 30% of nu-e fraction is indicating. So remember, this is 1/3, so that's what the 30% comes in. But it's not a very strong constraint. I will see that it will vary in the future. But anyway, so this is also an indirect way of testing the identity of the neutrino sources. And finally, one very important advance, and I won't say much in detail about this, is the multi-messenger detection of the first neutron star merger. And you see that we expected some objects to emit neutrinos, electrons, photons, neutrons, protons, all at the same time. And the first time we've actually seen this is in one neutrino, the first neutron star merger. And the idea here is just imagine we have the full like a film that has 3 reels, and some information, or say one color, is stored in each one of the reels. So we will get some information from each observation, radio, infrared, optical, X-rays and gamma rays, or neutrinos, and in gravitational waves as well. But we will only get the full picture if we combine. So this is what happened with the observation of GW1708-817. This is the first neutron star merger observed in gravitational waves and also in multi-messenger observations. So we saw it as a gravitational wave event. We saw it in optical bands and in radio and infrared. We saw it in X-rays and gamma rays. We did not see it in neutrinos this time, though, but we expect that it will happen in the near future, maybe with some other neutron star mergers. But then that's what gave us the full picture of what was going on here. And in fact, this discovery, this first observation, produced one of the most, to me, beautiful pictures that I've ever seen in a scientific paper. This is a single event seen in gravitational waves, in gamma rays, what is this, GLP? That's I'm not sure what this is. It's optical, I believe. X-rays, gamma rays, UV, optical, infrared, radio. So you saw the same thing in different wavelengths of light, gravitational waves, and we just were missing, in this case, neutrinos. So we expect that to happen, hopefully, the next time we see this kind of mergers. Okay, so I've spent a long time talking about astrophysics, so I'm going to have to rush through particle physics. That's the second side of the coin. But so you've seen that there's a lot of things that we don't know about astrophysics, the astrophysics of the sources that are making neutrinos. So does it make sense to try to extract neutrino physics at the TeV to TeV range? And I want to say that the resounding answer is yes, and that we can already do it today, and we are doing it today, but it's hard, and we can look like this. So we have to be careful with all the uncertainties. Okay, so there's a lot of different things we can test: cross sections, neutrinos of interactions, scattering of galactic dark matter, neutrino decay, dark matter decay, neutrino electron interactions, Lorentz invariance violation, stellar neutrinos. For me, the exciting thing about this test is that they were proposed for decades before the detection of high-energy neutrinos by IceCube, but today we actually have data. And so we can turn, and we are turning these predictions into data-driven tests. And we're actually putting these models to test. So one way to organize this vast landscape of theory models of the understanding model neutrino possibilities is the following. We put our favorite models, or some of them are very popular, of new neutrino physics on the page, and some of them will act at the production stage, so at the sources themselves. Some of them will act during the propagation of neutrinos from the sources to the Earth. Remember, because we have long baselines, long travel times, even tiny effects can compound and become observable by the time the neutrinos reach Earth. And some of them will act at detection, so at the Earth or at the detector itself, at IceCube, for instance. Not only that, we want to see how each one of these models can affect the four main high energy neutrino observables that we introduced yesterday. So the energy spectrum, the arrival directions, the flavor composition, and the arrival times. And we have standard expectations, as we said yesterday, for each one of these four observables. So we see a deviation from the standard expectation, then we can attribute it, we're careful, to one of these models. So each one of these can actually affect one or more of these four observables. So this crazy spidery-like map, it might be intimidating, like the Eye of Sauron, but I like to think it's, as a theorist, I like to think about it otherwise. And if you've read The Never-Ending Story, you know that this is the Orin is the talisman upon which you can wish for anything that you want, and that is kind of what a theorist would like in this case. Have a vast landscape of theory models that we can test with actual data. So let me be a bit more precise about what I mean by testing particle physics with high energy neutrinos. And the fact of the matter is that numerous new physics effects grow like this as a function of the neutrino energy to some power, and here is just a number, and multiplied by the distance that the neutrinos travel over, and some coupling constant. So this is a very generic form of the effects, and particular instances are, for instance, neutrino decay, where the dependence is 1 over E, some kind of Lorentz invariance violation, CPT odd one, when there's no energy dependence, and when there's energy dependence, the CPT even Lorentz violation has a positive exponent here. If we have PeV neutrinos traveling over gigaparsecs distances, that means that we can test the value of this coupling to be about 4 times 10 to the minus 47 in these units. And that's a very tiny number. And not only that, it's an improvement of several orders of magnitude over existing limits that were set with lower energy neutrinos, in particular atmospheric neutrinos and astrophysical ones. So that's why it makes sense to try to use astrophysical neutrinos to test high energy neutrino physics, because it allows us to test even smaller couplings than previously. And as we showed a slide ago, neutrino physics can affect any one of the main observables associated with neutrinos, in spite of all the nuances of poor energy, angular, and flavor reconstruction in the detectors, and of the fact that there are several astrophysical unknowns that are out of our control. We need to account for this, and in spite of accounting for these, there's still valuable data that survives the uncertainties. Okay, so I will show you one example because otherwise I will run out of time, and that is measuring the high energy neutrino cross sections. So this is a pretty well-known plot from the particle data group, and you see the neutrino nucleon cross section divided by neutrino energy. That means the neutrino proton or neutrino nucleon divided by the energy as a function of neutrino energy. And all of these points are points coming from accelerator experiments. So to the left, there was nothing until fairly recently, and then Coherent measured the coherent neutrino cross section. And to the right, there was also nothing above about 300 GeV until also recently, and IceCube allowed us to extend this plot. So just to get a feeling for what's going on here, at low energies up to about 1 GeV, the interaction is called quasi-elastic scattering. You might have seen it before. Neutrinos interact with with neutrons and turn them into protons. Antineutrinos interact with protons and turn them into neutrons. And then at slightly higher energies, the neutrino, the incoming neutrino, has enough energy to excite the nucleon with which it interacts. And then when it de-excites, it emits a pion, and it's called resonance scattering. And at energies above a few GeV, the dominant interaction, the dominant cross-section, is called deep inelastic scattering, DIS. And that's when a neutrino is energetic enough that it will see the quarks and gluons inside a nucleon as point particles and interact directly with them, break up the neutron, the nucleon into final state hadrons and create either final state charged leptons or final state neutrinos. And that's the same kind of process that IceCube, if you remember, uses to detect neutrinos itself. Okay, so we're going to center on this cross-section because we're going to be at about here in energies, actually about a lot more to the right, because we're thinking about, we're doing the measurements of the cross-section with TeV to PeV astrophysical neutrinos. And the way to think about how to do this is by going back to what we said yesterday about the transparency of the Earth to neutrinos. And again, let's put our detector here, like IceCube in the South Pole, and have an isotropic flux of neutrinos arriving at the surface of the Earth. So equal intensity coming from all directions in the sky. If our detector is in the South Pole and we are using fairly low energy neutrinos for the purposes of astrophysical ones, then neutrinos will reach the detector from all directions, roughly with the same intensity. They won't get stopped by going through the Earth because the cross-section of neutrino-nuclear interactions is fairly low. We expect the neutrino cross-section to grow as some power of the neutrino energy, and that power is roughly 0.3. But at below 10 TeV, the chances of a neutrino interacting is not that much. So we expect the number of neutrinos coming from above, we call the downgoing neutrinos, to be about the same number as the number of neutrinos coming from below. We call them upgoing neutrinos. So that ratio is about 1. Above 10 TeV, though, because the cross-section grows with neutrino energy, the Earth is no longer transparent, and some of the neutrinos are being stopped, the ones that are coming from the opposite side of the Earth. And therefore, when we do the same comparison between upgoing and downgoing neutrinos, we no longer get 1, but we get some exponential function of the neutrino-nucleon cross-section. And that is roughly how we get a handle on the neutrino-nuclear cross-section at TeV energies, at PeV energies, by comparing the number of upgoing and downgoing neutrinos. Of course, we do it a bit more carefully than that. We take into account all the different directions, but there's a couple of things you need to know in advance. You need to know the matter density inside the Earth, and for that we use a very popular model called the preliminary reference Earth model. It posits that the density of the Earth inside the Earth is layered, and towards the center of the Earth is higher, of course, and then it becomes closer to the density of water at the crust. We can take that, and if we want to guess more or less what we should obtain, we can take one of the models of the neutrino-nucleon cross-section that have been worked out in the literature as a function of energy, and see what we should expect if we have neutrinos coming from different directions with different energies, knowing the matter density inside the Earth and knowing what their cross-section is. So this is not a measurement. This is just trying to find out how more or less neutrinos should be suppressed as a function of energy. And so we take those two ingredients and we calculate the attenuation factor. So this is how much an incoming isotropic flux of neutrinos that arrives at the surface of the Earth would be suppressed depending on the direction along which it's coming to the detector located here in the South Pole for different energies. So you start with 1 TeV. Again, at 1 TeV, the cross-section is very small. And remember, this attenuation factor is like e to the power of minus cross-section. So the attenuation is very small. That's why the e to the minus power of the cross-section is about 1. The flux is not attenuated. Whereas if we go to the opposite side of things, if we're talking about 10 eV neutrinos, then the attenuation is brutal, and this suppression is 0. So it's killing the flux for all of the neutrinos that are coming from the opposite hemisphere. And in between, we have of course in between suppressions. Okay, so we know how that looks. We can actually plot it now in 2D. This is again the incoming neutrino direction. This is coming directly from above. This is coming directly from the opposite side of the Earth. And this is roughly the neutrino energy in the y-axis. And the darker the blue, the stronger the suppression due to neutrino-nuclear interactions inside the Earth. And one more thing you should take into account here is that actually our detector is not on the surface, it's ice cube. So it's buried 1.5 kilometers underground. That's why if we have neutrinos incoming from directly above our detector, they still need to go through 1.5 kilometers before reaching the detector. Whereas if they're coming from the opposite sides, from the North Pole, they need to go through twice the diameter of the Earth before reaching the detector. Okay, so again, downgoing neutrinos, the ones that are coming from above, are the ones that have a positive cosine of the zenith angle. These ones, upgoings are going through the Earth and have a negative cosine of the zenith angle. And the horizon is this line at 0. When the energies are low, or where the traverse path of the neutrino is not very long, the Earth is transparent. So the attenuation is close to 1, in which case because this attenuation multiplies the flux is unmodified. On the opposite side of things, if the energies are very high, or the travel path inside the Earth is very long, then the Earth is opaque, so the attenuation factor is suppressing the flux completely. So now we can actually use we can overlay. I think I'm missing that slide here. I'm sorry, but we can overlay actual ice cube events on top of this plot and do an actual comparison of the downgoing and upgoing neutrinos in a proper statistical analysis. And without assuming anything about the neutrino-nucleon cross-section, we leave the cross-section as a free parameter and try to extract its value. And when we do that, we actually make a measurement of the cross-section. What you see here is the cross-section in the y-axis, the energy of the neutrino in the x-axis, and these blue points over here are our measurements of the neutrino cross-section above 10 TeV from the method that I was just showing, and it's based on 6 years of ice cube data. It's coincident, or it's in agreement with the expectations from the standard model calculations of the cross sections, which is this orange band, and it's also in agreement with a different analysis made by ice cube itself. That's the green band over here. But we have still no handle on what happens over here at even higher energies, and that's something we're working out at the moment. But okay, one cool thing here is that you remember this particle data group plot where all the points were coming from accelerator experiments. This is the cross section divided by energy, and the energy in the x-axis. This is from using data from the 70s onwards. Now we can actually add a couple of points over here, or 3 points over here. Yes, the error bars are huge because we're basing our analysis on very few events, and we're splitting those events into 4 different energy bins, but still it agrees with the predictions of what the deep inelastic scattering should look like. So we're extending the PDG plot using the first TeV to PeV neutrinos. Okay, now I'm gonna have to jump over other examples, unfortunately, but I want to show you one thing about the future, and then I will stop there. So we've been talking so far about what's going on now, and I showed you this picture earlier with all the different sources of neutrinos and the experiments that are targeting them. And in particular, we've been focusing on the high energy and ultra-high energy ones. And I will say a bit more about ultra-high energy ones in a moment. But in the next decade or so, we expect to gather more statistics about the TeV to PeV neutrinos. And we expect to discover neutrinos of 1,000 times higher energy, so ultra-high energy neutrinos. But on the other side of things, we also have synergies with lower energy experiments that are going to happen also over the next decade. And these experiments, Juno, Hyper-K, Dune, they'll help us in reducing uncertainties, for instance, the mixing parameters that we need to reduce in order to make studies of particle physics at the highest energies. So I like to think about the future as resting on top of three pillars, which are the following: build bigger, build different, and work together. So let's very quickly go through each one of them. Build bigger, that speaks to increasing the statistics of the TeV to PeV neutrino observations that we have so far. And those are the ones that we have been talking about. And IceCube will continue running for at least a few more years. So we'll gather more statistics, but that's not the only experiment that will be out there gathering statistics. And IceCube will hopefully be extended. So in the next 10 years or so, we expect IceCube to be upgraded into IceCube Gen 2, which should be about 5 times larger than IceCube. The Baikal experiment, which exists now, is also in the process of being upgraded. Antares in the Mediterranean Sea should be superseded by KM3net, also in the Mediterranean Sea. And there is one extra detector that might come online in the Canadian, the Cascadia Basin in front of Canada. So we will have 4 detectors. Gen 2 will still be the bigger one, but the other ones will be at least as big as IceCube. With that, we can actually improve our point source limits from, in the case of IceCube and the northern sky, from this line, which I showed you earlier. So this is how well we can, this is the sensitivity to the neutrino emission from a single source. We can improve it by 1 order of magnitude to over here. And of course, the improvement depends exactly on where the neutrino source will be positioned, but it's roughly about an order of magnitude. Not only that, but we will have similar sensitivity to point sources also in the southern sky, because KM3net will be in the Mediterranean Sea, in the northern hemisphere, which means it will be sensitive to sources in the southern sky. So the second pillar is build different. And I've been talking about very briefly only about ultra-high energy neutrinos. And these may come, these are EeV neutrinos, so 10 to the 18 electron volts. And these may come directly from the sources or be produced along the way when cosmic rays interact with the photon backgrounds. So there's a host of experiments targeting these neutrinos, targeting their discovery. And that's a whole different conversation that we can have. They use either detection of, they can detect them either inside ice of water, like IceCube is doing now, like Antares is doing now, or we can use a different technique, and it's detecting air showers in the atmosphere induced by the interaction of neutrinos, either underground or in the atmosphere itself. One of the most promising techniques is involving radio, and that's actually what's more in being developed more strongly at the moment. That's, remember, neutrinos in IceCube are detected by the light that they induce. They, in some cases, when the neutrinos are very energetic, it's not only light that can be emitted, but also radio emission. So there's different strategies to detect that radio emission. And in particular, the projects that are more advanced I'm going to focus here at least are RNOG in Greenland, IceCube Gen 2, which also has a radio component, Grant, and Poema, which is not a radio detector, it's a detector of fluorescence light from space. So just to give you a feeling of how this is going to look possibly in the next 10 to 20 years. Again, this is the flux of neutrinos in the y-axis, neutrino energy in the x-axis. This is the latest IceCube measurement. These are upper limits on ultra-high energy neutrinos coming from a variety of experiments. You see here Auger, which is a particle detector in Argentina, cosmic detector in Argentina, sorry, and IceCube. Those have the best limits so far. This is the prediction of what the flux of ultra-high energy neutrinos could be. You see that the prediction is extremely uncertain. It covers a very large band of fluxes, all this gray space. And that's because it depends on properties of the ultra-high energy cosmic rays that are very uncertainly known. And you see some of these here. So the properties of the cosmic rays determine the properties of the neutrino emission, of the neutrino flux, and we don't know them very well. So we have also models that can even leave this space. Fortunately, these detectors that I've been talking about are being built to target even very small fluxes. So we have a chance of discovering these ultra-high neutrinos, and that's exciting for the next decade. And finally, work together. That speaks to the fact that in the next 20 years, A number of detectors are going to be built and will exist concurrently. So the exposure, or as you said, the detector volume is going to be growing, and by 2040 we should have a 16 multiplicative increase in the detector volume to detect TeV to PeV neutrino emission, and that allows us to do a number of things. But just to focus on one of them, we can join them all together, these 4 detectors that are targeting TeV to PeV neutrinos. We call this plenum, planetary neutrino monitoring system. So if we use the combined information of the 4 of them, we can improve how well we can, for instance, characterize the diffuse neutrino flux. And this is just a simulation, of course. With current IceCube, we can measure the spectral index of the neutrino energy spectrum and the normalization of the neutrino energy spectrum, like the blue line at 95% confidence level, assuming that this is the real value, of course. With plenum, we can do much better, and we can reduce that space, the contour, to something a lot more concentrated around the real value. Actually, this is even conservative. Our latest simulations are a lot better than this. So joining forces in the future is going to be key to improving, not gradually, but improving substantially. Okay, so just to close things, what now? Some of you in the audience are theorists, some of you are experimentalists. So you just keep in mind that this is an ongoing process. Theorists will hopefully give experimentalists well-motivated target sensitivity to aim for when designing new experiments. Experimentalists will temper the expectations of theorists and tell them what exactly is doable and what not, and hopefully also provide information in useful form to make predictions. But we've come a long way. So today, as I said at the beginning of the lecture, we're here. We've discovered the first few TeV to PeV neutrino sources. In the next 10 years, we expect to see more sources and characterize the diffuse neutrino flux more precisely. By the 2030s, if we're lucky, and we're planning for that, we could discover EeV neutrinos. But what comes after that, I don't know. And I'm happy to say I don't know. And that's going to be part of your job. So hopefully we'll be able to take you over here, but it will be up to you to decide and to figure out what to do next. All right, thank you very much.
Thank you very much, Mauricio. So please, I ask to the audience to mute your microphones and give an applause to Mauricio, please.
And remember, you can still register for our school up to today if you're interested in following it next week.
Yes, yes. Thank you very much. So, question, please. Don't be shy. So meanwhile, to encourage the students to do questions and see that there are no silly questions, I am going to do a silly question.
Of course.
So the silly question is, if you were an extraterrestrial intelligent life living out in the other side of the galaxy, what kind of particle will you use in order to communicate from one side to the other?
Well, interesting. Yeah, I have conflicting opinions on that. So yeah, I mean, if you shoot neutrinos, then it's they won't get stopped. But first, it's difficult to make an intense beam of neutrinos. Second, it's hard to detect them, so you need to rely on your listener to detect them. I guess what I would do is not necessarily try to communicate that way. If I want to make my presence known, I would just transmit in the water band. So that's just 21 centimeters, normal electromagnetic emission. If I'm being passive about making my presence known and I'm an advanced civilization with my Dyson sphere, I would just let the heat excess the excess heat of my heated up Dyson sphere signal others that I have produced a Dyson sphere. I don't need to transmit anything. I just allow the components of my Dyson sphere to radiate in infrared. If I actually want to send an encoded message, well, then that becomes complicated. And I don't know what the best strategy would be. I would still think electromagnetic emission and not neutrino emission is the best way to go.
Okay, yeah. I don't know. I just wondered that if I want to communicate, I am sure that it's not going to be possible that the other civilization is going to reach me, because we are millions of years late. So.
Yeah, I mean, another argument that I've read somewhere is you should send, or one strategy you could adopt is send a message to others or broadcast a message when you know that there is a high chance that others are looking at a particular thing happening. So if you have a very advanced civilization that knows that there's going to be a neutron star merger, and other civilizations might be interested in looking at that phenomenon, then broadcast a message roughly from the position of the neutron star merger, because people will be looking at it anyway.
I see. So I am looking for that in 2040 you will discover in the neutrino detection some message.
Well, I mean, some of the people in the audience might have read a book called His Master's Voice by Stanislav Lem. It's like Carl Sagan's Contact, but gone wrong. And the message that they receive in that book is messaging neutrinos, and it doesn't go well.
Okay, I see.
It's a science fiction book, by the way. So I'd recommend if you want to know what would happen to a message receiving neutrinos, yes.
Thank you very much. I didn't know. I will read. Yeah. So questions in the chat. It is from Felipe. Do you want? Okay, so question. Yeah.
Should I read it, or?
Please.
So it says, what would be the impact on model building in particle physics if we discover and measure neutrinos with energy at EeV? Well, that depends. So we do have predictions about how these neutrinos should be made by normal standard model processes, and that if we do see neutrinos of EeV energies, then we know with a certain number of neutrinos at EeV energies, we probably can confirm that the production of neutrinos is occurring according to our standard model expectations. Something that we're working on is related to that. So what I was showing you how we have measured the TeV to TeV neutrino nucleon cross-section using IceCube data. In the next decade or so, if we actually see EeV neutrinos, we can do something similar, but it's more complicated because the EeV neutrinos really don't go through the Earth, and they don't even go through 100 kilometers of Earth. They get stopped very far. So we don't have that many neutrinos to work out a cross section with, and that's something that my group is studying. But that would be a cool thing to do, because then you can measure the cross section at EeV energies. If there's anything new there, like a new mediator or a deviation from standard model expectations, then you might be able to see that if you are lucky enough that you have sufficient events. It's going to be tricky, but it's certainly possible.
Thank you very much. More questions? Andrea, please.
Hey. Well, I read a while ago, I mean, like a couple years ago, about something that I'm not really well documented. I don't know how to say it. Read about, but are there still any experiments looking for neutrinoless double beta decays?
Oh yeah, no, there's many. Yeah, that's super hot. So let me give some background information for the others. So we don't know whether neutrinos are their own antiparticles or whether the neutrinos and the antineutrinos are different particles. And in the first case, when they are their own antiparticles, we call them Majorana, and if they are different, with the neutrinos and the antineutrinos, we call them Dirac. And that's important because that is connected to how neutrinos get their masses, which is not apparently like how the other particles in the standard model get their masses. So knowing whether they're Majorana or Dirac tells us what mass granting mechanisms are more viable. One way to find out the nature of the neutrinos, whether they are Majorana or Dirac, is by looking for neutrinoless double beta decay. And this is a process wherein you have a beta decay that occurs twice, but you don't get a neutrino out of it because the intermediate neutrino that you would get from the first beta decay gets annihilated in a way with the second neutrino that you would get from the second beta decay. That's very roughly how it occurs. So you get two beta decays without any neutrino being emitted. But that only happens if the neutrinos and the antineutrinos are their own antiparticles, their own particles, the same particles, sorry. If they're Dirac, then that cannot happen. So there's many experiments looking for this. And as you can imagine, it's a difficult process. First, because it's two beta decays. Just looking for regular double beta decays with neutrinos is difficult. Looking for double beta decays without neutrinos is exponentially more difficult. So you need to have the right kind of isotope, radioactive isotope that decays with the right energy that is detectable by your instruments. They're very precise experiments going on. And there are many. Let's see, what is the leading one now? Oh, what is the name? That's escaping me. Yeah, I don't remember now. But sorry that I don't remember the names. Catherine. No, but Catherine. Wait, Catherine is to measure the tritium decay of
HEMA,
the mass of the
perhaps.
Sorry.
I remember HEMA.
Yeah.
They are the old ones. I don't remember the new ones.
I don't remember the new names. I'm sorry, but Catherine is not that. Catherine measures the mass of the neutrino by tritium decay. But there are many ongoing neutrinoless double beta decays. I'm sorry that I don't remember the names at the moment, and that is a hot topic of research for sure. It's an important thing to find out.
Thank you.
Thank you. Which could be the course into improving our experiments, our current experiments, or the ones that we have already planned, the ones you talked about?
For neutrinoless double beta decay?
Yep.
I think that the main problem that they have is backgrounds, as usual. So I don't know exactly what their backgrounds are that are not allowing them to get better sensitivity. But in general, there are some intrinsic processes that are that cannot be eliminated away because of the way these detectors are built. That is not allowing them to get better in their sensitivity to the lifetime of decay by a neutrinoless double beta decay. I couldn't tell you exactly what it is. Karen says Nexo there's a paper by Nexo today, so maybe you can read that. Nexo is one of the experiments that is looking for neutrinoless double beta decay, or will look for neutrinoless double beta decay. I don't remember exactly what the precise backgrounds are, but it's certainly the backgrounds that are not letting the experiments do this very, very delicate measurement.
All right. Thank you very much.
Thank you.
So let's say America.
Yes, hello.
Hi.
Hi. So Mauricio, do you think that with the future PV and EV neutrino detections, will it also be possible to test relic neutrino flux or infer about that?
Well, not quite. But this is a this is a complicated question, a complicated answer. So this answer has 3 parts at least. Yeah. Okay, the first part is the following. You have EeV neutrinos, so neutrinos with 10 to the 21 electron volts. Actually, you need a bit higher energies, but if you have very, very high energy neutrinos, those neutrinos can interact with the neutrino relic background very, very feebly by exchanging normal standard model bosons. And in principle, you could see a cascading down of particles coming from those interactions, and you could see excesses in the gamma ray flux, excesses in neutrinos at lower energies, etc. But I think in order for that to happen, you need neutrinos of 10 to the 25 electron volts. So it's like brutally high. We don't expect this to exist to start with. So that's the first part. That's a very direct way of testing the existence of the relic neutrino background. Unlikely. The second part of my answer is what if you had an extra mediator? So we're talking about neutrinos interacting with a relic, EeV neutrinos interacting with a relic neutrino background, not by the normal standard model boson, so not by Z, not by W, well, Z, but by a new mediator. That mediator, in principle, could couple strongly to the neutrinos. And if that were to happen, then you could have resonant interactions, for instance, between the high energy neutrinos and the relic neutrinos. And those are called sometimes secret neutrino interactions. And we've looked into that, and we're looking into that at EeV energies now within my group. So you could have features in the spectrum of EeV neutrinos that look like dips in the flux where the neutrinos disappear completely. And that's because the EeV neutrinos interacted with the low energy relic neutrinos, and they got dumped down at lower energies. So you left a deficit at high energies. It's like an actual dip in the spectrum. And if you look for those, they could be signs of secret neutrino interactions and indirect probes of the relic neutrinos. But again, this is a beyond the standard model way of testing the relic neutrinos. So it is certainly attractive. That's why we're working on that. But yeah, bear in mind, it is BSM. A more robust way of doing it is actually to measure the relic neutrino background, not by EeV neutrinos indirectly, but actually measuring the 0.1 millielectron volts relic neutrinos. And there's an experiment that's trying to do that. It's called Ptolemy. And the way it works is you have Ptolemy built, I think Ptolemy is built with tritium, if I remember correctly. And this tritium at nuclei are essentially wanting to decay. And when a neutrino, a relic neutrino, comes in and collides with one tritium, it makes it decay. So if you see a decay of tritium in your experiment that is faster than you would expect without relic neutrinos around, then you could attribute that to the existence of relic neutrinos. That is very roughly how the experiment works, and it's more complicated than that. That's an experiment that's been in development for a few years. It's still in development. As far as I know, it continues strongly, but it's a very difficult experiment, as you can imagine. You're trying to detect neutrinos of 0.1 millielectron volts. We have trouble with detecting, well, not longer, but we took a while to detect the CMB, which has about the same energy. So detecting neutrinos with that energy is terribly difficult.
Thank you.
Thank you.
Thank you. So one last question, otherwise we will close. Karen, please.
Yeah, I just wanted to, since the last lecture by Mauricio, and I hope this question is okay. If no, you can decline. That's totally fine. But maybe like your experience as someone who did their undergrad and even their master's in Latin America and who got like international experience just until like their PhD and then like a postdoc and now as a professor, what do you think is importance of like creating like international collaborations within the community and like the differences between you being a professor in a country that is like not in Latin America?
Well, I haven't. That's a good question. Thank you. I haven't had the experience of being a professor or a postdoc in Latin America. I cannot directly compare. But in reality, the main difference is that on the whole, there's typically more research money in Europe and the US than there is in Latin America. So that makes a lot of things easier from the point of view of logistics. To the that includes like hiring people and buying stuff and going to conferences, etc. It all becomes easier as far as I understand. But from my own personal experience, one thing that is absolutely clear to me, and it's probably already clear to all of you, is that talent has no country and it appears everywhere. And I've seen that from working myself with students from back home while I was the postdoc and now as a professor. I've seen it over years. My first PhD student right now at NDI is Peruvian. So, you know, I'm Peruvian. And all other students here are very international, and many are from Latin America. So it's only a matter of, let's say, the ecosystem of research that exists in each country that is different. And my one recommendation is just take the best opportunities that are out there, but whenever you can, and you can make an effort, just try to give back something to your home place. And that's, I mean, I try to do it in different ways. I organize seminar series all the way to today. I give talks there whenever I can, because, you know, it's a way to improve things back home. And you cannot change the science policy of your country, certainly, but you can open doors for people as being abroad, and that is rewarding. I can say that the second, probably on par, the thing that I like the most about doing physics, or other than discovering stuff occasionally, very occasionally, is seeing the people I work with, or the people that I mentor, learn and start doing things by themselves. And when you see that physical insight grow in them and they start to think about the problem by themselves, that is very cool. So whenever you can do that, being abroad in any small measure or big measure, do it. Yeah.
Well, thank you very much. So
thank you.
Please, I would like to ask to the audience again to mute your microphones, and thanks, Mauricio, for these wonderful lectures and this last message that we take with very warm hearts. Thank you very much.
Thank you.